Hello. So I thought we could work through an example here. Um, so the following situation is posed. I have a picture here. It's better than my attempt at a diagram. But you're supposed to find the velocity of A, sorry, not A given, of A, comma. So find the velocity of this point, given that the velocity of B up the wall is 3 meters per second. So the thing about this one is A, so when I show you the picture, you'll get a better view. But the idea is that this is a AB, link AB or rod AB, whatever, is a fixed object. And as B goes up the board, A is dragged along a plane with a slope of 35 degrees. And at the instant we're talking about, the angle here is 45 degrees. The length between A and B has a distance of 7.2 inches. So we want VA. Now, well, let's switch over and we'll take a different view. I'll show you the an image that I took a picture of. Okay, so hopefully you can see the idea here. The ramp goes up at 35 degrees at the instant they're talking about in the problem, or we're talking about. The angle up here at the top is 45 degrees, and the length of the rod is 7.2 inches. This point we're going to call A, and the slider we're going to call B. Okay. Okay. So how would we do this? Well, we're going to use the method of instantaneous centers to do this. So first thing we have to do is kind of estimate where the instantaneous center could be. And I need to give myself a little bit more room. So hopefully you can remember this 3 meters per second. We're just going to give ourselves a little bit more room. With the velocity of A. So to figure out the instantaneous center, I'm going to use the fact that I know that the velocity at B is along the wall. I know the velocity at A is along the wall, and I want to draw their lines of action. Now, I'll use this fancy line tool. See if I can manage that. Okay, the line tool says it should be somewhere up here, and this one should be somewhere over here. These two lines are perpendicular to each of the two velocities, and consequently, it must be that the instantaneous center is over here. So about this point, we know that at this moment, both of the points undergo a rigid rotation, a pure rotation about this point. So we can say that VB equals omega cross R, and it would be from the instantaneous center to B. And similarly, we would have VA equals omega cross RA, I see. And the two omegas are the same. That's the whole point of using the instantaneous center. It's a common angular velocity about that point. All right. So the plan is to use the fact that we know VB, and we can do some trigonometry to find RB from the center to find omega. And then once we have that, we will plug it into here, take this as a known, look at the geometry to figure out this, and then get our answer. Okay, so that's the general plan for what we're going to do. Now, I wrote this out as a vector equation, but really, we could do this one with scalar quantities just as easily. So if I do that, I want to look at my triangles here, though. Actually, let's go back and do some trigonometry. Because this angle is 45, even though my artwork doesn't show it, this angle should also be 45. And because I know this side is 7.2 inches, I know that this side, I know that RBIC should be the square root of 2 times 7.2 inches. Okay, so that's one thing I know. And I'm going to have to also do some trigonometry to figure out this length. Oh, sorry. And when I plug in numbers, this is 8.7 inches. Okay. Now, to figure out this length, I note that, well, let's think about this for a second. I know that this is at 35 degrees, but the rod is at 45 degrees, which means this is 10 degrees, which means that this is 80 degrees, or equivalently, I could say that this must be 35 degrees. So that's kind of helpful, because then I can use, so on this side I have RA from the Instantaneous Center, and I know I can use the law of sines here. So I can say that, for example, I could say that, hold on, let me make sure I got that right. Did I foul that up? So I've got 45, 85. If I foul that up, 45, 85, that'd be 125. Oh, I fouled that up. This is 55 degrees. Okay, so if this angle is 55 degrees, I can use the law of sines to figure out what the length of this side of the triangle is. So in particular, I have that RAIC over sine 45 must equal 7.2 divided by sine 55. Therefore, RAIC must have a length which equals 6.23 inches. This was in inches. Okay, so we know the length of the sides, and that's going to be all pretty much everything we need, because we're just going to work this out using scalar quantities. So we don't really need vector information. All right, so we know that the velocity of B was 3, but that should equal omega times RBIC. So I get that 3 equals omega times hold on a second. I'm afraid I messed up my velocity. I'm terribly sorry. Let's go back. I wrote the wrong number down, I think. And didn't write it. Anyway, the velocity at B is supposed to be 10. I think I wrote down 3, but if in case it should be 10. Sorry, I got cross with the example I was just doing in my notes. So the velocity is 10 at B. So now I can write that as 10 equals omega times RB IC, and that number was 8.7 inches. So I get that omega equals, let's see here, so that's going to be 10 divided by 8.7, 1.15 radians per second. All right, now that we know omega, it's pretty easy to work out the speed at A, because the speed at A is just going to be omega times R A I C, and we just found this number a moment ago. So this is 1.15 times, go back, see what we wrote down, 6.23, and we get 7.16. And it would be inches per second if we were to keep all the units. There you go. I apologize for fouling up the velocity on the one side. I've been doing a lot of examples back to back to back, and I'm getting the numbers kind of confused in my mind. So let's recap what we just did. We had a problem. We had a rod that was at a point sliding up a ramp. We determined the center of the instantaneous center of the motion to figure out where it looked like a pure rotation. Once I found that point, I could use knowledge of the velocity at one point to figure out omega, and once I had that in trigonometry, I could figure out the velocity along the ramp. Okay, so hopefully that was a helpful example. I've got another one here that I'll post as well.